Okay, folks, so these notes here are something that I put together and recorded last night, but unfortunately I completely failed to record the audio in a way that is useful. So I'm just going to give you very quick talks through this. We'll expand on it in various places, but this is just the gist of what this experiment is about. And I just want to start out with this part right here, which is essentially your background. This is what you did back in Chem 110, assuming that you took it here. You may have, if you took it elsewhere, you may have done something similar, but it's pure stoichiometry. We just, to remind you, a titration is just simply measuring with this burette, measuring a volume of something like you would have done sodium hydroxide with a known concentration in molar or moles per liter, and you would have measured milliliters, but volume in units of liters, which tells you the number of moles of sodium hydroxide it takes for a reaction. And from that, if you know the stoichiometry of your reaction, we'll figure out how much sodium hydroxide is needed to get to the point where, let's go with, say, HCl here, that we're titrating the HCl. We got a certain amount. We find out how many mils of our known sodium hydroxide it takes. Tells us how many moles of HCl there are, because one sodium hydroxide per HCl. And we can use that, getting the number of moles from our known substance, to find out all sorts of stuff. We did like a percent concentration of vinegar, and we also got the molar mass of a unknown acid back in the Chem 110 experiment. Okay, so that's a reminder of stuff that you knew how to do or you did at some point, whether we need to knock the rust off or you remember it well. We'll come back to at another point. But what we're doing is basically sort of taking this another step to find something a bit more out about our what's being titrated, other than just how much of it is there, what's its concentration, and so on. Okay, and that's going to be its behavior in terms of equilibrium, specifically the Ka, the acidity behavior. Okay, so essentially what we're doing, let me just backtrack very slightly to this experiment. And if you remember what happens, you add this sodium hydroxide into your acid that's being tested, and what you're looking for is that at some point you're going to get to a point where it goes from this colorless to pink, because we've got this phenolphthalein indicator in there, which is colorless in acidic solution, and we're going to have an acidic solution as up until we've added our one equivalent of sodium hydroxide. And then once we've got to the point where we've added exactly the same amount, the tiniest bit of sodium hydroxide after that is going to take us into basic pH, and that's where phenolphthalein is pink. So what we're really looking for is this sudden change in pH that happens just when we had a tiny last little bit of sodium hydroxide to take us to exactly, we've had the same amount as the amount of acid that we started with. And that's the general principle, and we're just looking for that change to pink. Okay, but we can sort of look at this a little more detailed by using a pH meter, which allows us to basically break the titration down into a series of steps, sort of about a milliliter at a time, each time measuring the pH as we go along. And for a strong acid, looking at the green here, for a strong acid, what happens, and again, I'll go back over the math and sort of what the calculations are and so on at another point, but basically as we go along, we're just adding, say, milliliter samples of sodium hydroxide. Let's say I've got my endpoint is going to happen at 20 mils. So each milliliter, we're taking away a 20th of the acid. And so our pH is going to sort of increase a little bit. Remember, less acid means higher pH. It's a bit counterintuitive, but it's what it is. And then as we get close to that equivalence point, we do see this kind of curve upwards, which is actually partly due to dilution, but it's nothing to worry about too much. It just kind of heads upwards, and we get to that equivalence point here, where if we've got precisely the right amount of OH minus to have neutralized, react with all of the H3O plus, then we would just have neutral water in pH 7. But typically what happens is, because it's very hard to hit exactly that point, we usually go over a little bit. And so once we're past that endpoint, as I said before, we get into where it's basic, because we've got an excess of hydroxide. And so we can visualize exactly what's going on. We're going through is just getting a little less acidic, a little more basic as we add base, but the H plus is getting absorbed, and once we run out of H plus, we get this sudden change in pH, and that's where our indicator changes color and so on. So that, again, there's a little bit of math that it would help to go through, but that's what we would see for any acid that is a strong acid. So HCl here, nitric acid, perchloric acid, HI, and so on. So sulfuric is a little bit of an anomaly, but typically strong acids, you're going to see this behavior, because when they get into solution, this is their definition, they turn entirely into this H3O plus, and that's what's actually doing all the reaction. So because it's always the same thing, the curve always looks exactly the same. So to cut a long story short, what we're actually going to be measuring is the curve that you get when, instead of a strong acid, you use a weak acid. And the standard is acetic acid. That's what all the instructions are about, though I think I may offer to those of you who are feeling a little braver a couple of other things that I would be interested in exploring how they would go in the context of Chem 111. So if you're up for something just a little different, do please let me know. But anyway, the idea is we're again going to just collect these points going along this titration, and as you can see, the shape is a little bit different. You should in class have done some calculations about, because this is not H3O plus here, it's better described as being all most representative of what's in solution for a weak acid is that it's HA that's reacting with the hydroxide. And you should have done calculations of what would the pH be at that initial, before you add any sodium hydroxide. What would it be? It turns out it's different at the equivalence point, because it's a basic salt. We talked about that in the problem set last week. It's a basic salt, so you end up with a basic endpoint, and you may or may not have heard about the fact that at this half equivalence point, this would be 10 mils. Here, you have this property where the pH is actually equal to the pKa of the acid. And one way of measuring them, for example. But there's sort of a lot to be learned about what's kind of going on in solution just from what's happening here. Now, so to sum up, week one would be to actually just set up the pH meter, which, as I've mentioned in my email, looks, based on the manual, it looks worse than it really is, but I can easily expand upon that given a little bit of time. But it's pretty straightforward. We're just going to set things up. We're going to measure out some acid. Got a burette full of sodium hydroxide that I will already have found the concentration on. I will have done the standardization for you, and we're going to just basically step through adding a couple of mils at the beginning and then sort of slowing down, adding a mil at a time as we go through, and just basically take the points to construct that curve, and then take those data, put them into Excel, create the plot, and that's week one. It's really quite straightforward. But then we have to think about what happens with and revisit those math calculations that you hopefully have done in class. But I will not say more about that at this juncture. That's basically, if you sort of read like the worksheet that there is, the basic idea is that once you've got that plot and you've got those data, that we're going to take some points, so randomly here, here, here in this region called the buffer region, and do a bunch of calculations to extract the Ka out of these data. And again, long story short, it's cumbersome, it's clunky. Doing this all with on paper like this is going to be a very onerous or tedious task, I think. And so what I have in mind is basically I'm just going to show you how Excel can make that a much easier pursuit. And I think you've heard me before talk about how I think learning a bit of Excel is useful. But anyway, I am thinking through what exactly I want to do with the analysis, but that's over a week away from today. So the first place to just steer you is simply this basic idea of what the experiment is about. And I'll get back to you with more details as they become available. Help me, I'm stuck here. There we go.